much things to talk about. So you know, chapter 5 we finished doing last week. We talked about the harmonic oscillator. And harmonic oscillator is the second model we encountered in this class. So the first one we still remember is called the Parity box. So harmonic oscillator is the second one. Of course, we mentioned before, when we talk about any microscopic system, we care about energy and wave functions. That's the two things. And one more thing for translation within this system, the new thing called selection rule, which kind of requires for some translation to happen and forbids. And some other translations are forbidden by according to this rule. Okay, and then we talk about even functions to simplify rate growth. Okay. So the first one, just a review about classic pictures of harmonic oscillator. I believe most of you have learned in your physics class to like a picture like that. So our subject is connected with a spring and fixed on the wall and vibrates. So if, let me ask you, so what is called the harmonic oscillation?
If it oscillates.
Everything can oscillate, but not every oscillations are treated as harmonic.
Oh, because it's the function. Is the right
like sine, right?
Yeah.
But if you go back to the very beginning, so it tells you actually the force created by the oscillation satisfies Hooke's law. So if the force, as you can see here, they satisfy this relationship, we call this what oscillation is a harmonic oscillation, and we know it's just idealized model again. Do you still remember the first idealized model we encountered in this course is what? That never exists in the reality. The first one. This is the second one.
Is that
The very beginning, chapter 1, beginning of chapter 1. Black body. The black body is also an idealized model. Here, harmonic oscillator is also an idealized model. It never exists in reality, only by approximation. Okay. So classical pictures. So here, I want to talk about classical pictures here. We'll talk about energy as well. As you know from your physics class, EK is just 1/2 mv squared, which you can rearrange to this form using the P as a linear momentum. Okay, and potential energy we derive it becomes 1/2 kx squared, where the x is the displacement of the subject, and total energy, of course, is the kinetic energy plus potential energy, and we'll give you 1/2 Ka squared. Here A is amplitude. Okay, so here S is the displacement. Here A is the maximum displacement, which is defined as amplitude. Okay, and you can actually draw the relationship between each energy with the displacement here, or the location actually. Here's not the location. So here, this one will be the minimum displacement, one amplitude. This one the maxima, another amplitude. There are two bonds here. And this is how the kinetic energy change, is how potential energy change. Okay. But if we add the two together, the energy is always a flat line, which means the energy is conserved. Okay. For harmonic oscillator, energy is conserved. So we call this as a conservative system. Okay, it's just recall from your physics. That's what I learned. I believe what you learned before, and this is classical pictures. But here what we're going to learn in chapter 5 is actually different from this picture, a little bit different. Okay, so then we talk about quantum mechanics. As we know, when we talk about quantum mechanics, the first starting point usually, in order to derive the energy and wave function, is Schrodinger equation. And for Schrodinger equation, the Hamonic operator, represented the total energy operator, contains two terms: the kinetic energy operator plus the potential energy operator. And the operator on the wave function gives you the total energy times the wave function. Okay, that's how you set up. And we know, for specifically this case, harmonic oscillator, the V, so the V operator will just potential energy, right? So 1/2 kx squared. And the kinetic energy, not special thing, you just put the kinetic energy is operated here, but pay attention here. I used mu here to represent the reduced reduced mass. Okay. If just one body, just add. But think about one body there that cannot vibrate. If you do not attach to a wall, it must be two things that vibrate. Okay, so that's why we choose reduced mass. Okay, and then you can solve this very rigorously, which is not required for this class. In theory, you will get energy states, I mean the expression for every energy state, and the expression for every wave function at each energy state. This is how we just go through the, piping in the box, right? So the same thing here, but except the derivation here is really tedious. Okay, so any questions about this? So if no question, let's first take a look at the energy states here and then talk about wave functions of harmonic oscillators. Okay, the first part about energy. So that diatomic molecules, okay, diatomic molecule, we can assume it behaves as a harmonic oscillator. Okay, but in fact it's not. But we can assume that it's like this, that vibrating this way. Okay, they're connected by a spring. But in fact, for diatomic molecules, this one should be just the balance, the chemical bond between the two. Okay, so if you assume that it behaves as a harmonic oscillator, the energy you will get from Schrödinger equation is this. So here the E unit in energy, in joules, equals h nu times n plus 1/2. And you can also convert the energy unit to a wave number, right, by dividing hc. So you will get E tilde, which means energy is in the unit of wave function, sorry, the wave number. And then you change the nu to the wave number here, the other part are the same. Okay, those are just the unit. Okay, if you change the unit, sometimes you change the notation. And some textbooks they use G, the same thing. Okay. So here, the blue part, nu here is vibrational frequency, which contains two terms here. So this one is quite just constant. It's not quite interesting. The first term is force constant, which is very important for describing the diatomic molecules. Okay. The second one is reduced mass, and I believe most of you know how to do that. Right? For a two-body system, what is the reduced mass?
M1, M2 over M1 plus M2.
M1 times M2 plus M1 divided by M1 plus M2. Okay, so sometimes, trust me, you're pretty nervous in the exam and you kind of forget which one is on the top, which one is on the bottom. So how can you determine? Let's say you just remember this one is M1 times M2, another one is M1 plus M2. But which one I should put on the top? Which one should I put at the bottom? Well, by telling the unit. Okay, the reduced mass will give you 1 unit.
Kilograms.
Or something reduced to mass, right? Let's say kilogram.
Because it would be a kilogram squared over kilogram.
Oh, exactly. So it must be kilogram squared over kilogram. In that case, you can get kilogram. So that's why you get a product on the top and the each on the bottom. Okay. So based on the vibrational frequency, or later we'll say based on the vibrational spectroscopy, it can tell you the force constant of the molecule. That's a major application for vibrational frequency, vibrational spectroscopy. Okay. This one, as I mentioned, the omega with the tilde means the vibrational wave number. So you convert the frequency to wave number. You still remember how can we convert frequency to wave number?
It's over C.
Which one over C?
The frequency.
Like this. Okay. Because E is what?
HC.
HC mu. Okay. So sometimes those related to those conversion would be very familiar with. Last one, vibrational quantum number. Okay. But starting from which number?
0.
We know they are integers. Starting from 0. Okay. And in your textbook, I want to really emphasize on that. If you check your textbook, you actually it writes in a different way. And most other textbooks also use this notation. They change the quantum number here, not using n, but using v, the small letter v, to indicate this is the vibrational quantum number. So they choose the first letter v, vibrational. Choose v. Okay. Then if you do that, you will see this is new. This is v. They're pretty similar. Even though they print on the paper, they're pretty similar. And for some of you, if your handwriting is not quite good, okay, maybe the first line you are pretty clear they're different. But after several lines of derivations, you start to think, okay, this one is actually the same thing as this one. So I will get v squared plus 1/2 v. Okay, so that's why I want to give you two suggestions. The first suggestion is do not use v, but use n in your homework. The second one is if you really want to follow the style of the textbook, make sure you write the two letters quite different. Okay, personally for me, I would write neo as that and v as this. So you can pretty easily tell the difference. But whatever, you can use different ways for you to tell someone like that. Okay, neo is whatever. But derive your own style to distinguish the two letters. They're quite different, okay? And also when you read the textbook, just pay attention. Sometimes the two letters under the printing on the paper, the printing format is also pretty similar. Just be careful about that. Okay, so the energy level diagrams is actually like this. So it looks a little bit complicated, but anyway, so if you go step by step, let's say the first one, this curve here, doing 1/2 kx squared will give you a curve like that. And we know potential energy equals 1/2 kx squared for harmonic oscillators. Okay, so actually this curve will give you the potential energy distribution. So with respect to what? Your x-axis, intermolecular separation or displacement, whatever. It just talks about the dynamics. Or the location is something like if you grab two molecules, two diatomic molecules like this, A and B. Okay, we can actually, because they are vibrating, actually both atoms are moving. But we can actually think we fix A and we vibrate B. So the distance between A and B actually change. So the x is actually the distance. Intermolecular distance or separation. Okay, let's use the potential energy. And we can actually plug in the n number and the neo for given molecules. And you can evaluate energy as well. Here the energy means total energy, right? So for n equals 0, pay attention, the first quantum number for vibrations is actually 0. Okay, you will get a number. For n equals 1, you get another number. N equals 2, n equals 3, n equals 4. So those lines here represent the total energy. And this line represents the potential energy. Okay? So here the first one, if we plug in n equals 0, and if we work out the frequency, you will get 0 point energy, which is not equal to 0. And we have some questions in the midterm ask you to interpret this result, which we'll talk later. Okay, so here it is like we have a non-zero 0 point energy. Okay, so pay attention, there is something tricky. So although the name is called 0 point energy, but actually it's not so for harmonic oscillators. For the next chapter, you will see actually it's different. So also they can, the vibrational is also have energy states and the molecules. So the molecules, here we're talking about the molecules, not the electron. We're talking about the molecules, that atomic molecules together, they can also transit to higher energy levels or just going back, okay, like this. And you can evaluate the energy difference between each camp here using the equation I showed before, that all equal to H0. So they're identical. If if your transition is involved two adjacent energy levels. If you go from here to here to here, actually get doubled. But later we will see, based on the selection rule, this is not. So if you are close the energy to make the transition, this is not allowed. It's forbidden. So only by one step, or going back one step. So the energy difference are always the same, they're identical. So it looks like the energy levels here, also the gap is also the same, right? So it looks like a beauty of each layer. Perfectly, the gap is the same for every energy level. This looks a little bit different from 5 megabucks and also from hydrogen atom. So 0-point energy, let's pick it up and talk about the first thing. So the questions in the midterm ask you what is 0-point energy, right? What's your answer?
Half H nu.
The what?
1/2 H nu.
Yeah, but interpret the meaning. What is 0-point energy? The first question asks you to evaluate, you already get a number. Now question B, what is the average? What is the 0-point energy?
The lowest possible energy.
The lowest possible energy for the harmonic oscillator. Or another form or another version is the energy with the vibrational quantum number equals 0. Or the ground state vibrational energy for a harmonic oscillator. Those are correct. Okay, all of them are okay, which is based on your idea. But this is the perfect one. It's the perfect one. The second one, the third question in the midterm tells you, oh, well, this is the direct result of Heisenberg uncertainty principle, but why? All right, did you get the question? Do you think you get the question? Let's do it. Okay. For 0-point energy, we don't talk about energy here. So energy is composed of kinetic energy and potential energy. Okay, so here we use an average value, whatever. Okay, you can use just an absolute value, but for absolute value it's a little bit tricky. Because for different harmonic oscillators, they have different energy. So here we choose the average one. The average 0-point energy, of course, is composed of average kinetic energy plus potential energy. And based on our classical pictures, we know the average EK equals this one, average potential energy equals this one. Okay, so the existence of 0-point energy means the 0-point energy is non-zero. So this one simply gives you non-zero value. And let's take back to look at the uncertainty principle. It talks about this. Right, it's talking about that, or it's square root it. But anyway, we can square it and get this one. And this one, based on what you learned in chapter 4, can be expressed by this expression. And do you still remember how can we simplify this expression here? There are actually two terms which equal 0.
P squared and X squared. Well, P squared.
This one and that one. Okay. Simply because the average location is 0 for a harmonic oscillator, and the average linear momentum is 0 for a harmonic oscillator. And the proof is in the textbook. You can go back and check. So simply we know, based on uncertainty principle, the two things, the product here equals this two product. And we know uncertainty principle tells you this two cannot be 0. Okay, let's take it back here. Take a look back. If 0-point energy is 0, what will happen? What will happen? If 0-point is 0, what will happen for the first one? We have two squares here, right? Actually, I made a mistake, sorry. This two should be, that's okay, yeah, that's right. If this one is 0, we know this is a kind of positive number. This is another positive number. So two positive numbers together equals 0. That indicates the two must be 0 simultaneously. So it cannot be this one is a negative. So the two energies made up together equals 0, means 0-point energy is 0, then This one must be 0, this one must be 0. Okay, if you plug in here, 0 times 0 will give you 0. And this value is uncertainty principle. That's why we call this the direct result of uncertainty principle. Do you get it? Okay, or you write something different. We will see. We'll start grading this afternoon. We'll see what you wrote on the paper. Okay. Let's do one exercise. Please label the potential energy, kinetic energy, and the total energy for a state with quantum number n equals 4, and this intermolecular length equals A in the following figure. So now it's not the separation, it's not the length, so actually the figure shifted a bit, but it's still the same shape. So here is the location L equals A from this location. Okay. But I ask you to find, or actually label in the figure, where is the potential energy? And where is the kinetic energy? Where is the total energy for this state n equals 4? After the potential energy will be easy to identify. Well, first question is I want you to find. So there are several lines here, right? Each one represents an energy level. Which one n equals 4?
The top one.
Okay. Oh, don't do that. Okay. 1, 2, 3, 4. Because of what? The first one is what? N equals 0. Yeah, so n equals 0. So n equals 4 actually. This one. At this length A exactly means this point. Okay, so now the question reduced to this. What is the kinetic energy for this point? What is the potential energy for this point? And what is the total energy for that state? So this actually represents a state. And you can actually label it in the figure. You don't need to do any calculation. Need more time? Which one? C. I mean this one?
Yeah.
And total energy. What others? Alright, the first one is easy, I think. The potential energy is easy because they ask one question. What is the curve represent? What is the curve represent? That's actually potential energy. So whether you know the energy state here or not, you actually can read the potential energy because we already give you x equals a. So if you read from here, you get this length is about potential energy. Okay. So you simply draw a line, you read from this point, this will give you potential energy. Okay, this is read from the curve because this curve means potential energy. And the second easiest way to identify, easiest thing to identify is total energy. What does those lines represent? The what? The energy levels, right? The energy levels based on the magnitude of total energy. So this one will give you energy, the total energy actually. So actually the hardest one to identify, kinetic energy, now becomes very easy to be identified because you already know E, you already know potential energy. And we know kinetic energy plus potential energy must give you total energy. So the remaining part will be kinetic energy. Okay? Good idea? This is actually a practice to help you understand the energy diagram of a harmonic oscillator. Okay, where you can find those information. Okay, in reality, we know not everything behaves as a harmonic oscillator. Harmonic oscillator is just an idealized model. So we introduce a concept called Anharmonicity, which simply represents the deviation from harmonic oscillation. So this green curve is what we showed before, okay, the energy diagram for a harmonic oscillator. But in reality, most diatomic molecules behave as the blue curves describe, okay, which is not the perfectly matched with the harmonic oscillator behavior. But there is something, first thing I want to mention is within this very, very small region here, you will see actually the blue curve somewhat overlaps with green curve. Okay, because this part deviated a lot. This part deviated a lot. Only this tip here, quite close. And the physical meaning for the tip here is, this point means the equilibrium boundness, means no vibration. So if we think just a small vibration, just a small amplitude, the diatomic molecules still behave similarly as a harmonic oscillator. So we call the good approximation when first thing is V must be 0. So it must be in the ground state. The second one is when R is close or approaches equilibrium boundness. Okay, so if you do not vibrate too hard, and if you are in the ground state, well, we can treat you as the harmonic oscillator. Is the first thing. The second thing is you can see there are two letters here. One is called DO, one is DE. Okay, so the first one, the DE means theoretical dissociation energy of the diatomic molecules. Why? Okay. So when the energy, potential energy becomes flat, the simply represents this molecule as dissociated. So the potential energy will no longer change. Okay. But within this level, we call the dissociation level. So then the energy from the very beginning, the lowest one, in theory, the lowest one is not based on quantum mechanics again. Based on in theory, the lowest one until reach this level, the energy difference is called the theoretical dissociation energy. It's somewhat like the ionization energy we talk in the hydrogen model. Right? You have an atom at that energy state and you ionize it to the infinity. The same thing here. You have a diatomic molecules on the ground and you excite it to the dissociation level. So the energy we require is the dissociation energy. But you can see actually this one is called theoretical because it chooses this as the starting point. And what we talked before, the lowest energy for diatomic molecules is 0 point energy, which is there. So there's some gap here. Okay? So that's why people define another term from dissociation level to the first energy level here as experimental dissociation energy. That means if you do it, measure it experimentally, instead of getting DE, you get DO here. And based on the figure, can you tell me what's the relationship between DE and DO? For what? For the
it's the
difference. Okay. The difference between DE and DO is just the 0.8 energy. Okay. Clear, huh? Based on the figure, you can actually just read it. The last thing I want to mention is, pay attention, let's take a look at all those inner gaps. For the green one, what we mentioned before, is like a building. Every floor has the same height. Okay, exactly the same height. But how about the blue ones? They're not. And it becomes, with the quantum number increases, the gap becomes what? Smaller. So reduced, like squeezed. So energy gaps decreases when the N increases. Okay, so this is like what? I mean, this energy gap pattern is like which one we mentioned? Hydrogen atom. Okay, hydrogen atom. So let's make a summary. We have three situations where the energy gaps increases. Energy gaps increase with increased quantum number, or remain the same, or decrease. Okay, let's say for the first category, what model can you think of which satisfies this? Great. How do you think about? Any more? Well, there's one we haven't learned. It's called rigid rotator. So rigid rotator also the increases. Okay, for the second category, just one example. We learned so far. Remain the same. Harmonic oscillator already talked about, right? For this. What about others? Anyone else want to give me the opinion? Energy gaps decrease with increased quantum number? One thing we already talked about just one slide ago. Yeah, one thing, Anharmonic Oscillator. Another thing is what we talked in chapter 1. The first question in your midterm.
Oh, is it the hydrogen?
The hydrogen atom. Hydrogen atom, based on Bohr model, the energy level being closer, closer, closer. Okay, that's why when you see the lines, it's getting closer, 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 closer. Okay. Second one, Anharmonic Oscillator. So pretty much represents some real diatomic molecules. Okay. Second part about wave function. So this is a normalized wave function which we got at from solving the Schrodinger equation. Okay. Looks really a little bit scary. But here, well, it's kind of the general form makes you feel scary. But if we take a look at this term here, this term called the Hamonic polynomials. Okay. And if you go back check your textbook, table 5.3 will give you several polynomials here. Well, those things you don't need to memorize them. Okay, those things you don't need to memorize them, and the relationship between all those things you don't need to memorize them. If we ask you some questions regarding this polynomials, we definitely will give you the expression. Okay, so if you substitute this one into it, and you choose different n numbers, you will get each wave function for each inner state, right? And let me ask you one more question. Which first n we should plug in order to get the ground state wave function? So which n? What is the n value for ground state?
0.
0. Okay, so in order to get the ground state wave function, we need to plug in n equals 0. And we will find the first one. the polynomial first one, pi being 2. So actually you can see this is 2 to 1. It's pretty simple. So those shows you the 4. The first 4 wave functions for a harmonic oscillator. Okay, and this picture shows the function, the figures of those 4 functions. So this one is the first one, second one, third one, fourth one, and the fifth one, the expression is one here. Okay, one more thing I want you to pay attention in. As you can see, this is the potential image curve. And some of you, I bet, you are thinking now, this curve is actually the boundary. Well, if that's the boundary, take a look at the boundary here. My question is, will the wave function be 0 at the so-called boundary there? Is 0? If it's 0, then it needs to return to the flat line, right? But clearly at the boundary here, it's still not back to the baseline. So then this results in another question. What are the boundary conditions for harmonic oscillators? Okay. What are the boundary conditions for harmonic oscillators? For polynomial box, 0 to A. For harmonic oscillator, simply by looking at this figure, where will the wave function be 0? Then that's the boundary. From this one goes to infinity, it'll be 0. Here goes to negative infinity, it'll be 0. So that's why we call it the boundary condition. So when you do the normalization or calculate the probability of whatever, now you provide something like that. Okay, the integral is like that. It's not no longer 0 to A. Okay, it's no longer. And by doing the product with this convex conjugate times the wave function itself, it will give you a probability density. And if you draw the probability density in the figure, is like this distribution curve. Okay, so again, it's the same thing as polynomial box, where you see the maximum value means the maximum probability density. Okay, for each energy state. Okay, and you can also, find some characteristics for each energy state, which we will not talk here. For example, for all the odd numbers, the maximum probability density actually, at least there's one in the middle.
Is there a reason that the probability density is larger towards the potential energy curve? You know, if you look towards E7 and 6, they're all even except the very last two are large.
That's kind of pure math things. So if you know the expression, you do this, you plot it like that. And this is close to what we'll talk here. Think about the probability density distribution for a classical oscillator. I mean, for classical pictures. You see the dash line there? That dash line represents the classical probability distribution. Well, it's not a flat line. It's still like this curve. But can you think of the y? The probability of finding that, let's see. If this is a 2 amplitude, the probability of finding that oscillator is still not a flat line like that. But why are the 2 bonds here, the probability is higher?
Oh, because it goes over and back when it oscillates, right?
Yes, it goes over and back, but you will reach every point. But why only at the 2 bonds, the 2 boundaries there, the probability is actually higher compared to in the middle?
It stops there? Is it hit 0?
No, it's not stopped here, but the velocity is 0. So at 2 bonds here, if near the bonds here, the velocity is slower. Especially at the middle point, the velocity is the maximum. So you can think about that. If you try to catch something, it's easier for you to catch it when the velocity is slow. It's harder for you to catch it when the velocity is the fastest one. So if you're pretty fast, it's pretty hard for you to catch it. But at 2 bonds, the probability is higher. Okay? And the same thing with quantum pictures. Well, what I showed before, you already recognize that the two bonds they have a higher probability. Still follows this kind of classical picture, but it's not constitutive, it's quantized. Okay, this is n equals 10, and also you can do n equals 50. Okay, n equals 50 will give you a path. And you can imagine when n approaches infinity, what will the picture look like?
It's a classical curve.
Then you just feed the same thing. Okay, the two they feed with each other. So now again, when the quantum number approaches infinity, we recover the classical pictures. The same thing with talking particle in a box. When the n goes to infinity, we recover the classical picture. Okay. Most examples in the quantum mechanics, well, if someone tells you, I want to tell the relationship between classical mechanics with quantum mechanics, the bridge is n approaches infinity. So once the n approaches to infinity, there's no quantization, just classical pictures. Okay, this is another example. The third one for harmonic oscillator is the selection rules. And selection rules, which is derived from time-dependent Schrodinger equation. And we know we don't care about that. So here I just give you the conclusions. And for you, you only need to memorize those conclusions. You don't even know how we derive it. Okay. And the selection rules applies for two different kind of oscillators. The first one is the idealized model, the harmonic oscillator. The second one is somewhat real model, is Anharmonic Oscillator. Okay. For the first one, it says in order to observe the transition or give you the intensity of the peak, it must be non-zero dipole moment change. Okay. In mathematical expression, the dipole moment change must not be zero. Well, do you still remember what's the definition of a dipole moment? You learn in your G Chem, you learn in your O Chem. Well, just think about that. We'll talk about that. I'll give you a picture, and maybe you can record from your various classes. The second one is the transition must be between adjacent inner states. That's what I said before. Your delta n must be plus minus 1. You must go one step and one step. One step up, one step down. You cannot get two steps. Okay. These are the two rules for harmonic oscillator. For anharmonic oscillator, the first one is the same as the harmonic oscillator. Okay, which must involve dipole moment change. It does not mean just dipole moment. There must be dipole moment change, but dipole moment must change. The second one is transition now can be between any states. So simply means delta can be plus minus 1, 2, 3, 4, wherever you want to go. It's like hydrogen atoms transitions. Okay? So back to the question, dipole moment. Can you recall from what you learned before? So it simply talks about a polarized molecule, with some part is highly positive, some part has electron rich, so it's partially negative. And then it will create the distribution of some charges within the molecule. And dipole moment is a factor to describe this non-uniform distribution of charges. So mu equals Q times R. Okay. The R is just a separation between the positive center with the negative center. And usually the direction, it is a vector, so the direction is point from positive to negative. Okay? So then based on this picture, and based on the selection rule, which means the dipole moment must change. To give you two examples. For diatomic molecules, we have two kinds of diatomic molecules. One is the homonuclear diatomic molecules, simply means the two atoms are the same. The second one is the heteronuclear diatomic molecules. The hetero one means they have two different atoms, and they can both vibrate. But my question is, which one you will be able to observe its vibrational spectroscopy? So once the two molecules they vibrate, can you tell? So So which one you will be able to see their transitions and give you the signal in the spectroscopy. We think about selection rule. Okay, let's assume they all goes from 1. Okay, delta A is 1. So they satisfy the select one of the selection rules, but another one requires the dipole moment must change. For this one, where's the dipole moment? For example, it means the dipole moment is 0. So whether you vibrate or not, think about that. You're still 0. There's no dipole moment for that molecule. But it's different from here. Here, because of different electron negativity or affinity, maybe A is partially positive, B is partially negative. So now they have the, let's think about that. Now they have separated charge center, and that is dipole moment. Okay. Now assume the two atoms vibrate. Once they vibrate, which one will change? The distance will change. Once the distance changes, dipole moment will change. So then you will be able to observe the absorption or emission from vibrational inert, the changing vibrational inert state. Okay, and you can observe the peak in the spectroscopy. Otherwise, it just it will not give you no peaks, but just pretty tiny peaks. And sometimes below the resolution, it just immerses in all the noise. Okay, clear about this? So for homogeneous diatomic molecule, you will not be able to detect its vibrational inert transition. Okay. So based on that, here we want exercise. Pretty straightforward. Since we have limited students, let's go one by one and tell you a bit. Okay? Have you finished reading the question? Do you have any questions about the wording or? So I assume you all understand, right? Okay. So which one you want to choose and tell us to read it? Choose A, and the reason is?
Well, because oxygen is more electronegative, so it's going to pull the electrons towards its direction because it's a Phillips-off tech. So it's the electrons.
So you want to say the dipole moment after can change?
Will change.
Will change, and will someone give you want to choose A, right?
Yes.
But why not B then? B also has dipole moments.
I know, but it evens out because not one.
Right?
It's a tetrahedral structure.
It's touching because it's going to cancel out. Because
It will not cancel
If
out.
they're all moving at different times, I know what you're talking about.
Yeah.
Like, they all, that's like an average. On average, they cancel out, but if they're
Yeah,
individually vibrating, they don't.
No, yeah.
okay.
Yeah.
Well, anyway, how about you? Right. A and B, right? A and B.
I think it's just A.
Just A?
Yeah.
Why you ruled out B?
Because of the structure, it cancels out like
Cancels out. Okay, let's go from here. Oh, too long. Too long. Any ideas? You want to say A and B and one for others?
I think it's B.
Why did you then rule out A then?
Because how would you get a pure rotational spectrum just from the moving back? Because it's a double bond between C and O.
Well, you can also rotate, so what can be a rotational spectroscopy?
No, it wouldn't be completely even, like a pure rotational spectrum.
Yeah, here I mean pure rotational spectrum. Exactly, pure. That means without non-original things. A and B. Same reason as others? No answer. A. Why? Because you randomly pick one? Alright, let's analyze this. Gabriel, you want to say?
So if you want a pure rotational spectrum, and you don't want vibration, you don't want to have a dipole,
Yeah.
right? So now, think about that. Which
Think
one
about
does not have a permanent dipole?
Which one? You want a pure rotational spectrum. You don't want a vibrational spectrum to interfere with the pure one. You simply means the vibrational spectrum for the four molecules, or for the correct answers, it must be
Zero.
no there, right? There's no vibrational spectrum there. That means it either violates the selection rule, or the dipole moment is just zero, it will not change.
So C would be.
Yes.
So now everybody figure out if you see it. You always focus on the dipole moment change, choose A and B, or which one. That's why last week in a reverse way, to not choose the one with non-zero dipole moment change. You choose the one with zero dipole moment change, that's C and D. Okay, so pay attention. Okay, all angular functions, last part, while we learning math, right? For all functions and even functions, my question is how can you prove them mathematically? Not by just pulling it out. Okay, pulling it out is one way, but in a real exam, you were not allowed to use any graphic calculator. But then how can you tell if a function is an odd function, another function is an even function? How?
The inverse,
Maybe
you evaluate the inverse x for the f(x) of the function.
you change the x to a negative x, right? You change the x to a negative x and see what may happen. And simply there are two possibilities. One is they equal to each other. Another one is they equal to the negative one. And the third one is, well, it's not equal to f negative x nor negative f negative x. There are just three possibilities. But this first two is kind of spatial. And we call this function as what? Fx is what? If satisfy this relationship.
Even.
This is called even. Then this is called odd. And this is called just a function.
Yeah.
Okay, it's not even nor odd function. Okay, so odd function, if you switch the sign of x, you change the sign of x, it will give you another negative sign out. That means it's odd function. Okay? And if you plot it, it's like that. And you can, based on the figure you will see, if we choose fx, and we change the sign of negative x, change the sign of x to negative x, and we give you f negative x. And because of the figure like that, they actually have different sign, but with the same magnitude. Okay, that's this one. So we say the plot of the odd function is symmetric about the original point. Okay, it's just about point symmetry. While the even function satisfies this definition, and the plot is like that. Again, if you change the sign of x, you read the fx, it will be the same. So f negative x will be the fx. It's just equal to each other. So now we call the figure of an even function as symmetric about the y-axis. It's just a line symmetry. Okay, this one is a point symmetry, it's right now. Okay? And we know if odd times odd will give you a function. Odd times odd, even function. Odd times even, odd function. Even times even, even function. How can you memorize it?
You're just adding this. You're adding the exponents.
That's still not the easiest one. I want to hear the easiest way to memorize this relationship. Well, treating them as the number. You're treating the odd function as odd number. Odd number times odd number, you do it 3 times 3. 9. 9 is that.
No, it's adding.
Oh,
It's adding.
So it's adding, yeah.
Yeah.
3 and 3.
3 plus 3 is 6.
3 plus 3 is 6, that we even. So, then it's not quite.
It is. No, look. So like, I'll show you. Odd plus odd. 3 plus 3 is 6.
Yeah.
Even.
But you need a change in the sign.
Odd plus even. 3 plus 2 is 5. Is odd.
Yeah. I mean, it's not quite straightforward, but just
Yeah, it is.
you need to change the multiplication.
Because you're when you multiply the functions, you add their exponents. So you're adding the numbers to create the odd or even of the function. That's how it works. I looked it up.
Oh, okay.
No, I definitely spent a long time figuring this out, and that's how it works.
Yeah.
Because that's how the
Yeah,
exponents
that's
add.
why.
So like x squared times x squared, even times even is 2 plus 2 is
2
4.
plus 2, yeah.
So
Yeah, right. It's like a power. But anyway. Well, you either just memorize it, or you find your own way to memorize it. So the easiest way is just give you like an even function is like x squared, like y equals x squared. Another one is the even odd function is x. So you use this two to try. So odd times odd is x cubed. Still not this.
Because odd
times odd is x squared will give you the even function. The x times x squared will give you x cubed is the odd function. X cubed times x squared will give x fourths even function. Okay. And the harmonic polynomials, which we'll talk about before, they are either even functions or odd functions. And they will make your integral in this chapter a little bit easier. Because sometimes, well, we'll talk about it in the next page, but here we focus on this. As you can see, the first 6 harmonic polynomials, can you tell me which 3 are even functions and which 3 are odd functions? So these 3 are, everybody be curious, these 3 are even functions, these 3 are odd functions. Okay. And why do we need to know that? The ending of this story is help you to integral. Well, if the integrals, you integral an odd function with the symmetric space, within a symmetric space. Here symmetric, I mean the 2 bounds, they are symmetric. They're from negative a to a, where a can represent everything. A can be 1, can be real a, can be b, can be infinity. A can be infinity as well. Okay. If you integral an odd function within a symmetric space, it's something like that. Because we know the integration represents the area underneath the function. And because odd function is symmetric about the original point, so the area, the absolute value for the area, this part and this part, they're the same. But they have different signs. In the green area here, the y is positive, so the area is also positive. In the yellow area, the y is negative, so the area is also negative. And if you combine the 2 together, they cancel exactly with each other, and you get 0. Okay. The second one is, now you integral an even function within a symmetric space. For this case, well, you cannot say it equals to 0. Because as you can see from this figure, they have the same sign. By the way, they have the same sign and also the same area. So when you integral within a symmetric space, you can actually reduce to half of the space and then put the 2 in the front of the integral. Like in here, you're from negative a to a. Now you can reduce to either negative a to 0 or 0 to a. So you just find the middle line and you cut it and put 2 in the front of the half of the integral. And that's it. Okay? So next time when you see this integral, don't ask us that you don't know the standard integral. Okay, so something like that, maybe y10. And this will be your left. Okay. In the final, well, sometimes we can give you the standard integral. to just kind of mislead you to do the real calculation and cost you a lot of time. And then you will shout after the exam, I don't have enough time to finish all the questions. Think about that. When you see that, 1 second you can do this per round. It equals 0. Because of what? All function for a symmetric space. If this is not symmetric, don't use that, okay? So if this is 0, that is not 0. Okay, it's not symmetric anymore, so it's not 0. It must be symmetric. Okay, so any questions? Any questions? If you have one question, holiday is coming on Saturday. Okay, I'm not sure whether you have any plans, but one more question.
Show me those cats.
Oh, I agree. Just one of the 3 monsters. Okay, so that's all for today's section.